G'day guys, today we're going to do an exam question which is asking us to factorize this particular cubic function over a complex domain. Now before we start guys, make sure you remember to like and subscribe to my channel. I'm only a new channel, so any new subscribers really does help put my videos out there to a wider audience. So let's get to it. When I'm asked guys to factorize cubic functions, I do have a very specific way that I begin these. So the first thing I'm going to do, guys, is I'm going to try and evaluate this function at specific points. These points being g of 0, g of 1, and g of negative 1. So I'm looking for whether any of these will make the function equal to 0. Now, guys, there are a few small tricks that I like to use in exams to make this process quite a lot faster. For the first one, g of 0, we can tell that this is not going to be equal to 0 because of the existence of this constant term at the end of our function, plus 20. Now, for g of 1, what I'm going to do is I'm just going to add up all of my coefficients, which include this constant term at the end. So what I'm going to do is I add up my coefficients being 1 out the front of the first one, 9, 28, and 20. And what we find is this doesn't equal to 0, obviously. So what we can say therefore is that g of 1 does not make the function equal to. And finally guys, let's try g of negative 1. And what I do with this one guys is I add together the coefficients of things with odd powers and coefficients of things with even powers, and I see if they're equal. So the coefficients with odd powers is the one out in front of the z cubed. So we have 1 plus 28, and the even powers is going to be the z squared and the constant term at the end. And what we find, guys, is that the even terms and the odd terms both add up to 29. So as a result, if we put in negative 1, the even and odd terms will cancel each other out. So we can say that g of negative 1 is equal to 0. So what this tells us, guys, is that we can take out z plus 1 as a factor, because when we substitute z equals negative 1 into this, it also equals 0. So just like if we were, say, fully factorizing the number 12, and we found that one of the factors was 3, what we would have to do is we would have to figure out, to fully factorize anyway, what the number remaining is after we've taken out 3 as a factor. So obviously, guys, this is a 3 times 4. So then what we could do, continue factorizing this part here. So essentially, guys, we're going to do basically the same thing here. The way I got 4 is I would have divided the 12, the original 12 rather, by the 3 that I've found out as a factor. I'm going to, in this case, get the original function and divide it by z plus 1 to figure out what the remaining part of the function is that I have to continue factorizing. So guys, like I said before, in order to find out what I have remaining after I take out my z plus 1 factor from the original cubic function, I need to find the quotient of the original cubic and z plus 1. So what I've done is I've actually got that division represented here, as well as the long division problem. Let's get cracking on the long division problem here. If you guys aren't aware of the algorithm you use to solve long division problems like this, or polynomial long division, I'll leave a link in the description below of a couple of videos in the back catalogue which explain how this polynomial long division algorithm works. But for those who do, let's just go through this as quickly as we can. So to start with, we take the first number in the polynomial and divide it by the first number in the divisor. So we have z cubed divided by z is simply z squared. And then we go z squared times z is z cubed. And z squared times 1 is plus z squared. And then what we do, guys, is we take the second two numbers from the first two numbers here. Z cubed take z cubed is 0. 9z squared take z squared is 8z squared. And then you bring down the next number, plus 28z. And then we repeat the process. We go the first number in the new polynomial, 8z squared, divided by the first number in the divisor. Z is equal to just 8z. Then we get this number and multiply it back through. So we have 8z times z is 8z squared. 8z times 1 is 8z. And then we subtract 8z squared plus 8z from the initial 2. So 8z squared, take 8z squared, again is 0. So hopefully, guys, you'll understand that the first two numbers should always equal to 0 because that's what you're dividing initially. So then we're going to go on to the plus 28z, take 8z is 20z. Bring down the plus 20. And we do the first number in the new polynomial divided by the first number in the divisor. 20z divided by z is just 20. And we multiply the 20 through. So 20 times z is 20z. And 20 times 1 is 20. Cool. So we then take 20z plus 20 from the original. And we are left with 0 plus 0. So that's another good way of checking whether z plus 1 is indeed a factor of the original function. But as you can see, because we're left with no numbers down here, it's 0 plus 0, we have no remainder. And as a result, z plus 1 goes evenly into this function here. So what can we do with this information? Well, we've basically just found out that once we take z plus 1 as a factor out of the original cubic, we're left with z squared plus 8z plus 20. So when we complete this quotient here, we are left with z squared plus 8z plus 20. Okay guys, so now all that's left to do is factorize the remaining quadratic. Now, in my opinion, the best method to use is completing the square when our solution is likely to contain complex numbers. So what I'm going to do is I'm going to set this quadratic, z squared plus 8z plus 20 equal to 0, and then I'm going to solve it using the method of completing the square. So let's get to it. So the first thing I'm going to do, guys, is I'm going to take the 20 to the right-hand side, and then what I'm going to do is I'm going to turn this z squared plus 8z into a perfect square. Okay, cool. So now what I've done is after taking the 20 to the right-hand side, and then making this z squared plus 8z into a perfect square, you can check my solution by expanding this bracket here. What I'm going to do now is I'm going to take the 16 also to the other side. So I'm going to be left with z plus 4 all squared is equal to -4. Cool. So if you've just been introduced to complex numbers, I feel like the best way to go about this so you don't confuse yourself straight up is to break this -4 down into 4 times -1. So let's just write that down to start with. Cool. So the reason I've done this is when I take the square root of both sides, it'll be easy for you to understand why I'm getting the complex number I out of this. So again, we take the square root of both sides and we're left on the left-hand side with simply z plus 4. And on the right-hand side, we're left with plus or minus the square root of 4 multiplied by the square root of -1. So if you've been introduced to complex numbers before, you will be aware that the square root of -1 is equal to the complex number I, or I is equal to the square root of -1. So when we're doing this particular problem here, we're going to say that z plus 4 is going to be equal to the plus or minus, the square root of 4 is 2, multiplied by the square root of -1, or I. Cool, so then all we have to do is take the 4 across to the other side, and we're left with z is equal to -4 plus or minus 2i. So basically what this means, guys, is that g of -4 plus or minus 2i will equal 0. And like we did in the original where we found that g of -1 was equal to 0, which corresponded to z plus 1 being a factor, when we found that g of -4 plus or minus 2i was equal to 0, this is going to correspond to z plus 4 plus 2i being a factor, and z plus 4 minus 2i also being a factor. So finally, guys, because I know all of my factors, I can finish this off with hence the original cubic function, z cubed plus 9z squared plus 28z plus 20 is going to be equal to our first factor, z plus 1, multiplied by z plus 4 plus 2i times z plus 4 minus 2i. And that, my friends, is the solution. So I hope the video helped, guys. If it did, give it a like and subscribe to my channel. I put out new videos on various topics as often as humanly possible. But in terms of this particular question, it is an exam question, guys, and as a result, you'd have to be able to do it fairly quickly. So all I can give you as advice is you're going to need to practice these ones a lot to make sure you can do them fast. Because in the grand scheme of things, this is not a complicated question when you're talking about sort of a calculus / complex numbers exam. So you want to be able to knock these ones over fairly quickly and with quite a high degree of accuracy. So the only way you can do that is practice, practice, practice. Keep bashing your head against the wall until the wall eventually falls down. But until next time, guys, just make sure you keep enjoying your maths, and I'll see you soon.